Okay, this is the second lecture on confidence interval estimation for population mean mu. In this lecture, we will assume that the population standard deviation sigma is unknown. Please go back to the previous lecture and make sure that you understand everything there, because this lecture will heavily depend on the previous one, because I'm going to skip the things that we already talked about in the previous lecture. So in this lecture, the most important thing is at the end that this table that you see here, you understand it perfectly. When sigma is known, this is what we did last time. Okay, so today we will do the case when sigma is unknown. When we have a normal distribution, then notice one thing here. First, when sigma is unknown, of course, you don't have a choice but to use the sample standard deviation instead of sigma. In all of these, of course, sigma is not given, so you use S from your sample, the sample you choose. And you can find the sample mean, and you can also, you know the sample size, n. So all what you need to know really from this lecture is how do we compute this thing that you see here, t sub alpha over 2. Of course, when we have a non-normal distribution, we will continue using z sub alpha over 2. So this new thing that we will learn about today, the t, it's called the t distribution, and it will have its own t table, just like the z had its own table, and also we had online calculator that helped us solve problems on how to find this z sub alpha over 2. We will do the same with t. Remember that for this z sub alpha over 2, we called it also z sub c, and you remember that c was the confidence level, and alpha that you see here was the significance level, and the relationship is c is 1 minus alpha, which means, of course, that alpha also is 1 minus c. Good. So if any of these things you forgot, you must watch the previous lecture. Okay, so today we want to understand the t distribution. Okay, and the same thing that we did, we will do for the t distribution. This t sub alpha over 2, we will also call it t sub c. Okay, it depends on the textbook that you're using. Some textbooks use t sub c, and some books use t sub alpha over 2. You just ask your professor or check your textbook to know which one of these two notations are you using. Okay, so the t distribution. Now, the stuff that I talked about is here already. There is one thing only that I just want to tell you from here, is that when the sample size is large, there is one thing that you can use, is that the population standard deviation becomes close to the sample standard deviation. Okay, so in this case, you will still use z sub alpha over 2 here, kind of assuming that what's given to you is sigma, not s. Yeah, but when do we use t is what's important. We use t in the following situation. So I'm going to just erase this and just tell you that the t is used when we have a normal distribution. Of course, first we choose, and from this normal distribution, we choose a random sample. And so we have a normal distribution and sigma is unknown. These two together, this and this, will require us to understand the t distribution and use it for the confidence interval. Okay, so what is this t distribution? And how do we get this t? That will be most of the lecture, talking about this specific thing. So the t distribution has many characteristics. One thing just I want to remind you, please always remember throughout this video that whether I write t sub alpha over 2 or t sub c, I mean the same thing. This is why this here, you read it also known as, okay? And the confidence interval will have this form. Okay, so who created this t distribution? It was an English statistician. His name is William Seeley Gossett, and he's also known as Student. This is his pen name. In his time, he was not allowed to publish his result with his name, for some reasons that you can read here in the history. But just see that he used the name student to hide his identity. And what was this man interested in? He really was interested in samples that had a small sample size, small n. So samples with small n. Small n, let's agree, it means n less than 30. Okay, so he was interested in what kind of distribution approximates samples that are small. And he constructed this t-distribution and called himself student, because he was not allowed to give his name. Okay, so before we understand the t-distribution, just you need to know that it's not just one distribution. There is a family of distributions that are parameterized by what we call degrees of freedom, and we denote it as df. This is degrees of freedom, and the formula for it is very simple. It's here. The degrees of freedom are n minus 1. So you take your sample size and subtract 1. So if your sample, let's say you had a sample of 15 people, this means that your degrees of freedom will be n minus 1, which is 15 minus 1, which is 14. There is an example that is given to you here. Please read it. So I'll say this is an assigned reading for you. But Le'anud actually told me that there is an easier example for you to understand. So Le'anud is going to give you this example. Suppose that you have a small classroom. So this example is to understand degrees of freedom, like what does it mean and why is it n minus 1. So suppose you have a small classroom with 6 students. Let's say that this is student 1, student number 2, 3, 4, 5, 6. When they come to class in the morning, they want to sit. And so student number 1, let's just say that she chose to sit here. You see, she had freedom to choose any of the 6 chairs, but she chose to sit on this one. Now the second one has also freedom. He can choose, let's say, this one. The third student can choose, has freedom and can choose this. The fourth also has freedom. The fifth also has freedom. He can choose this or this. So let's say that he chose this one here. Now, what about the 6th student? She has no freedom of choice. By this, I mean no degree of freedom. She cannot choose. She must sit here. This is why we will say that from this sample, we have 5 degrees of freedom. And so you will say, my sample size is 6, and I have 5 degrees of freedom. df is n minus 1, which is 6 minus 1, which is 5. This is Le'nud's example, and I believe that it makes sense to you now. So whenever you remember degrees of freedom, the easiest example is this one. Okay, so now let's go to Dismos and look at what does this t-distribution look like. So I'm going to open Dismos now. Let's open it full screen. Of course, here I put the normal distribution in black. This is the standard normal curve. Okay, it's the one here. And the t-distribution, I put it in green. But the t-distribution is not just one. I put the degrees of freedom, and the degrees of freedom are denoted by V here to make it easier for me to use Dismos. In fact, in many textbooks, they use, instead of writing df for degrees of freedom, they use the letter V actually. So I put it from 1 to 30, and I want you to see, first thing that you see before we start, is that the green curve, this t-distribution with 1 degree of freedom, you see that it's symmetric, and you see that it's bell-shaped, and the only difference between it and the normal distribution is that it's more spread than a normal distribution. You can see it has more variation than the black curve. Now, watch as I play the V moving from 1 to 30. Watch this now. Okay, I will play now. Look at what's going on. The spread is decreasing, and the curve is approaching the standard normal curve up to 30. We will stop at 30, but just know that when we arrived at 30, it almost is the same as the standard normal distribution. But if you really want to get the black curve exactly, the standard normal distribution, this degrees of freedom has to go to infinity. Okay, so when you can say that as v goes to infinity, the t distribution with degrees of freedom v approach the standard normal distribution. Very nice. So it has a lot of characteristics that you already understand. So let's go back to our notes, and we will look at something here. Of course, here I give you also the picture that you saw in Dismos, an approximation with different values of degrees of freedom, V. Okay, and here is the probability density function of the t distribution with degrees of freedom V. So this, we can write it, this is the function at x with degrees of freedom V is equal to, and this is the formula here. So you can write it like this. This is the probability density function. In order for you not to feel that this is difficult, by the way, you don't have to know this formula, but I will spend just a couple of minutes, maybe 3 minutes maximum, to make you just see that it's not that hard. Only you need to know that what you see here is called the gamma function. Okay, the gamma function, like this. Gamma function. It's one of the most important functions in mathematics, in almost all branches of mathematics. You see it in statistics, in probability, in mathematical analysis, in geometry, in physics, of course, you see it. You see it in all applied mathematics. It's good to know that there is a function called the gamma function. Now, what I want to do is to just show you what happens when we take 1 degree of freedom. What if V is 1? So let's replace 1 in this formula. So this will be gamma of, and now V is 1. So 1 plus 1 is 2 over 2, 1. Gamma of 1 over radical, this radical, V times pi. V is 1, so 1 times pi is pi, times gamma of V is 1, so 1 over 2. This one will be. And now let's write this one. This will be times 1 plus, now x squared over 1 is just x squared to the power minus, and then v plus 1 over 2, 1 plus 1, 2, over 2, 1, so to the negative 1. Let's simplify. This is going to be, now quickly I will tell you, gamma of 1, if you compute it, this is 1. Let's put it in another color so you do not distracted. Gamma of 1 is 1, and gamma of half is radical pi. You're not responsible to know it, but it's one of the most important values of gamma. Gamma at half is radical pi. Remember this one. But you only will need to remember it because L'Anoud will try to teach you something important about the gamma function later. Okay, but for now let's just check what this will be. So it will be 1 over, now you have radical pi times radical pi, so that's just pi, times something raised to the power negative 1 is 1 over that thing, so 1 over 1 plus x squared. So now this is our probability density function when the degrees of freedom are exactly 1. So what I'm going to do now is I'm going to graph this function and see if really it agrees with what we had before in Dismos with degrees of freedom 1. So let's see the function. Okay, so let's take the normal distribution out, and here I will do 1 over, it was 1 over pi times, then it was 1 over 1 plus x squared. Just to make sure, let me check. Where is it? Yeah, it's here. So 1 over pi times 1 over 1 plus x squared, yes. So let's see now. So in what color? No, I want to change the color, make it red. So you see, this red is the formula that we just arrived at when we put degrees of freedom 1. So let's decrease the degrees of freedom now to 1 and see if it agrees with our computation. Look 3, 2, 1. Oh, they agreed, exactly. So, okay, so if you take the red away, you will see the green. And if you take the green away, you will see the red. Okay, so they are the same curve. So this is nice to know, that the formula that I showed you is really the correct formula. Good. So let's now continue. La'noud wants you to look at the last 6 slides of this lecture, and she will be teaching you something very interesting about volumes of balls in high dimensions. Like as the dimension gets higher and higher, how do you find the volume of a ball? You know, for example, the area of a circle is pi r squared. Volume of a sphere is 4/3 pi r cubed. And then La'noud tries to show you what happens when we go to dimension 4, 5, 6, and something interesting happens there. Maybe we'll talk about it at the end, but you're not responsible for this. Just La'noud wants the students that are interested in learning more to see this stuff, okay? So now, to compute this t sub alpha over 2 that I told you about, or we call it also t sub c, in order to compute it, first you need to know what is the confidence level. I want 95% confidence. So immediately you will go and choose confidence level 95%. Just one thing, in this table, when you see one tail and you see 2 tails, this is something that you will learn about in the next chapter. So for now, you can just forget it. Just look at the confidence level that you're interested in, and then they're giving you the sample size is 12. If the sample size is 12, this means n is 12. And so how many degrees of freedom do we have? Degrees of freedom, always one less than n, so 11. So you'll go here and choose 11, because in the T table, they are giving you the degrees of freedom here, not the sample size. So you have to subtract 1. And then you move here and you move down, you'll get this number, 2.201. There is something nice. And of course, just before I show you that there is an online calculator for T, just notice that this is the T that we just computed now. Okay, so we needed 95% confidence. So our confidence in this case was 95. That's what was given at the beginning. And the degrees of freedom, we took 11 degrees of freedom. This gave us 2.201 from the table. You see, from the table, you put the 95 and you put the degrees of freedom, and then the intersection of them will give you the value of T that you're looking for. Okay, I want to show you, okay, it's on the second page. It's showing you that there is a website called statdistributions.com that allows you to find this T sub alpha over 2. So just one thing to notice, here they write something called p-value. You will learn about it in the next chapter, but for you, replace it with alpha. And remember, alpha is 1 minus c. So I will just tell you quickly. If they tell you we want 95% confidence, you know that c is 0.95. And so alpha, significance level, is 1 minus c, which is 0.05. This is why you see that we put 0.05 here, where you see the p. This p, just think of it as alpha, your alpha, or as 1 minus c, when they give you the confidence level. Let me just ask you quickly, what if the confidence level was 90%? What would you put here? You'll put alpha equals, yes, you guessed it right, 0.10. So 10% significance if confidence is 90. And if confidence is 99%, then what would be the significance level alpha? It will be 1 minus 0.99, which is 0.01. It's 1%. Okay, good to remember these 3 things, because most of the time we use 90, 95, and 99% confidence in most cases. So let us just check that our answer here, this 2.201, that we get it in the online calculator. So when we go in the online calculator, we need to remember that 95% confidence and 11 degrees of freedom. So let's go now. The calculator is here, so you put here, when you see p-value, let's just make it big or bigger. The p-value, you put alpha. But what is alpha? We know that C is 0.95, so alpha is 0.05. And the degrees of freedom, the sample size is 12, so we have 11 degrees of freedom. And keep it at 2 tails all the time, 2 tails. Okay, later I will tell you we will use right and left tails, but for now, for confidence intervals, always keep it at 2 tails. Look at the number that you got for T, 2.201, which is the same as what we have from the table. So great. Now you know that you can use this online calculator and you don't need to use the table. But the table, didn't you notice that it was very quick? Just immediately find the confidence level that you're interested in and the degrees of freedom, which is the sample size minus 1. And immediately you can find the intersection and get your T sub alpha over 2. Notice also that this, we call it also T sub C. Don't forget that. So you can say the critical value T sub C is 2.201. Or you can say the critical value T sub alpha over 2 is 2.201. Okay, and there are 2 tables. They are the same. I mean, this is the t-distribution table that I got from one of the textbooks, and this is from the other textbook. So check which one is in your textbook and use it. If you don't want to use it and you want to use the online calculator, that's perfectly fine. But please do what L'Anud is telling you. L'Anud is telling you practice using the online t-calculator on the previous slide. So here from the previous slide, you know that you go to this website, statdistribution.com, and you can use this calculator. For some of the values of the t-distribution table that you see here. So what I suggest you do, just like L'Anud told you, just pick some confidence level. Let's say you pick 90% confidence and you pick degrees of freedom 22. So this means your sample size was originally 23. Check that you get this number here, 1.717. Please do it now. Okay, check that you get 1.717. If you get it, then this means you know how to use the online calculator. Okay, last thing before we take a break is L'Anud is trying to remind you of something, that when do we use this t-distribution? So there are 2 places in this table that we use the t-distribution. So notice here the T sub alpha over 2, T sub alpha over 2, and as you know, in some books this is written as T sub C here, as T sub C. This is very important that you don't forget. Okay, that's why I keep on saying it a lot. Now, I will just take it out so that you're not distracted. So you see, if you have a normal distribution and sigma unknown. So she's trying to tell you here, population standard deviation is unknown. That's the same as saying sigma unknown. And population is normally distributed, normal. So these are the places where you use the t-distribution. And it doesn't matter, large or small sample, as long as your distribution is normal. Perfect. And of course, since sigma is unknown, you will replace it with the sample standard deviation S. Okay, so now we will take a short break, and I will you pause the video and I will continue in 3 seconds. Okay, so now I'm going to solve 2 examples and then we will finish. Then you'll have some exercises that you need to solve and send me your answers. So the first example, let us read it and write the given together. So how about this? You can pause the video, write the given, and then unpause to see if what you wrote is correct or not. So it says the waiting time of customers at a fast food outlet is normally distributed. From the beginning we are happy because this is normal distribution, so we know that we are safe now. So a random sample of 11 customers, so our sample has 11 customers, showed a mean of 2.2 minutes. So the mean here, x bar, that's the sample mean, of course, is 2.20 minutes, and a standard deviation of 0.35 minutes. Now, is this the population or the sample standard deviation? Of course, if you read it, a random sample showed and a mean and the standard deviation. So this means that this is the standard deviation of the sample, S. So this means that sigma is unknown. Now, S is 0.35 minutes, and we get from this that sigma is unknown. Very nice. And our random variable, we need to say that it follows a normal distribution. Let's just write, it follows a normal distribution. And what is our random variable here? Remember, from the question you can get it. It's the waiting time of customers at a fast food outlet. This is what is normally distributed. So what I suggest you do is this highlighted thing here, write x, say this is my random variable, x equals this, the waiting time of customers at a fast food outlet. And we know that x has a normal distribution. Our sample size is 11. Our sample mean is 2.20 minutes. And our sample standard deviation is 0.35 minutes. Last thing is find a 95% confidence interval for the mean waiting time at this outlet. So they want the confidence level to be 0.95. Okay, so 95% confidence level. Let's see what we should do in this case. So we have normal, sigma unknown, and sample size is small. So normal, let me just take this out. So we have normal, sigma unknown, and sample size small. So this means that I'm going to use this formula for the confidence interval. Let's highlight it, and we will write it here. So x bar, so we have mu is going to be between x bar minus t sub alpha over 2 s over radical n, and less than or equal x bar plus t sub alpha over 2 s over radical n. And notice that if your textbook uses c, you'll put c here. Instead of t sub alpha over 2, you'll put c. Okay? So now let's see. We have x bar, we have s, and we have n. All are given. So the only thing that we don't know is this t sub alpha over 2. But notice, I have the confidence level and I have the sample size. So you can say, let's compute now t sub alpha over 2 or t sub c computation. So let's see what it will be. Okay, so now n is 11. This means what are our degrees of freedom? This will be just one less than the sample size, so it's 10. Very nice. Degrees of freedom 10, and our confidence level is 0.95, which means that significance level is 1 minus c, so it will be 5%. Okay? So, of course, you can use c and degrees of freedom with the table, but if you want to use the online calculator, you will use alpha and the degrees of freedom. I'm going to use the online calculator. So, 10 degrees of freedom. So, I will put here 10 degrees of freedom, and this one, yeah, 0.05 for alpha. Okay, perfect. So my t value is in this case, so therefore t sub alpha over 2, the critical t value, which we can also call t sub c. I will keep on doing this so you always remember that we can use both notation for this, is equal to 2.228. Perfect. So we found t sub alpha over 2, and now we can solve the question. So we just need a regular calculator. But just before I use the regular calculator, let's just remember we have 10 degrees of freedom and 95% confidence. Let's just make sure that the table will give us this value or not. So 95 and 10, so you can say here 95 and 10 degrees of freedom. So look at what I got, 2.228. 228, yes. Or you can use, of course, if you're in this class, the class that uses T sub C, 95% confidence, level of confidence, and 10 degrees of freedom. So look, you get also 2.228. So just we know that our answer is correct. It's nice, just for the first time I do it for you. So you can say, therefore, mu is between something and something. Now I'm going to use a regular calculator to find these two numbers. Notice that the only difference is this is minus and this is plus. So we will use the calculator now. Let's put it here. So what is x bar is 2.20. Let's do the minus first. T sub alpha over 2. So open parenthesis 2.228 times, and I need a fraction. So I'm doing this one. S, now I want to put S. S is here, 0.35. So 0.35 divided by radical n. So radical sample size 11. Sample size is 11. Here you don't use degrees of freedom. Degrees of freedom only when you find t. Okay, so now equal. So I'm going to put it here. So I got 1.96, and then you have 4/8, so I'll make it 5. I'll do 3 digits. And then the upper limit for confidence, it will be when you put a plus. So this will give you 2.435. And that is our final answer. That we are 95% confident that our population mean is going to be between these two numbers. The numbers that you see here, 1.965 and 2.435. These are in what units? Of course, they will follow the same units as x bar and s, minutes. So the mean waiting time is between 1.965 minutes and 2.435 minutes. And just one thing, remember what we called this? We called it the lower confidence limit. And this upper one, we called it the upper confidence limit. Good. Let's check that our answer is correct. Just remember these two numbers, 1.965 and 2.435. Look, 1.965, 2.435. Okay, and this is the full solution. Now, I'm going to show you a surprise. This surprise will be probably a pleasant surprise for you. Let me show you something. So now there is actually a website that I'm going to show you right now, in which it computes for you the confidence interval for the mean when sigma is unknown, and it gives you t also. So let's put here, what's our sample mean? It's 2.2, remember? X bar is 2.2. And sample size, remember it was 11. All of this you can see here, n is 11, x bar, s, and alpha or c, depending on what the calculator takes. Now sample size 11, standard deviation is s, which is 0.35, and how confident do we want to be? 95%. So I'll put 95 and then calculate. Let's see what we get. Look at this. 1.965, yes, to 2.435. Yes, exactly. And let's put a very happy face that now you know that you can get this 95% confidence interval just by entering these numbers. Now there are limitations to this. For example, if we ask you to find, by the way, here t is given 2.23. Notice that it's the right value is 2.228. But here they're giving 2.23, so they're approximating t to 2 digits. It's okay. But sometimes we ask more conceptual questions. That's why some students ask me, if we have these calculators and we can use them, then why do you ask me to solve it this way, to do all of this? The answer is simple. You need to know the process. You need to know the concept so that you can answer more questions. Sometimes the question could be going backwards. I could give you the confidence interval and maybe I'll give you some of these, and I ask you what confidence level would give me this confidence interval. Or I ask about the margin of error. If you remember from last lecture, that's why I told you to watch the last lecture. From the last lecture, remember, margin of error is this part, the part that you add and subtract from the sample mean. So this is, we called it E, this part. Of course, in the previous lecture, we didn't have T sub alpha over 2, we had Z sub alpha over 2. Okay, and we didn't have S, we had sigma, because sigma was known, and so on. Yeah, but we called it the margin of error. Still, we call this the margin of error here. Okay, sometimes we ask you just find the margin of error. By the way, it's given here also. When you see here 2.2, just see what I'm making big. 2.2 plus minus what? 0.235. This 0.235 is the margin of error. 0.235. Okay. And here I show you, of course, I wouldn't just tell you in the video. Now, in your notes that you printed, you will see the website and you can go to it and practice on using it. Good. So there is a second question here. How about we solve this question using the online calculator? So we have, let's just write the given. You randomly select 16 coffee shops. I know my sample size is 16. And measure the temperature of the coffee sold at each. So I know that my random variable is the temperature of coffee. Okay, so that would be it. And X, of course, sample is small. So I'm expecting that this X will be normal. And here it's telling you. By the way, it's telling you approximately normally distributed. So you say X follows a normal distribution. In this course, if we tell you approximately normal, think of it as normal. Okay, you understand? This means that you can use everything that you know about normal distribution, even if we tell you approximately normal. But what's good here, I mean, not good, but it's what's special about this example is that sigma is unknown. Because here, if you read, the sample mean temperature is this. So this is X bar is 162 degrees Fahrenheit. And with a sample standard deviation of 10 degrees Fahrenheit. So S is given, not sigma. So this is 10 degrees Fahrenheit. And you know that here, this means that sigma is unknown. And it's unknown and the sample size is small, but the random variable is approximately normal. So this means that you can use the t-distribution. See, very nice. We can use the t-distribution. Now they're asking us for 95% confidence. So confidence level is 0.95. Good. I have everything now. I have all of the things that are required. And of course, being normal is required. So you can say, therefore, our mu, which is the population mean what? It's the temperature, the mean temperature. That's what we want to estimate. So the population mean temperature is between the lower confidence limit and the upper confidence limit. But what are they? Let's now use the online calculator. So I'm going to, let's first, we use green, and now we go to the second calculator that I showed you. By the way, this calculator also finds T for you, so you can even forget about this calculator. Okay, you can just use this for everything, the one here. So what is the mean that we have? Let's write it again. X bar is 162 degrees Fahrenheit. As the sample size here is n equals 16. And the sample standard deviation, even here they remind you, S, is 10 degrees Fahrenheit, 10. And I want, 95% confidence. Calculate. Okay, so let's see. The answer is in blue here. So I will write it. Let's write it in blue, just the same. 156.67 degrees Fahrenheit. And the upper confidence limit is 167.33 degrees Fahrenheit. But I'm not going to write degrees Fahrenheit. Just write it like this. And you understand it has to have the same units as the sample mean and sample standard deviation, of course. Okay, so let's check if our answer is correct. Just remember these two numbers, 156.67. You can make it, if you want to one digit, this will be 156.7. and this will be 167.3 if you want to one digit. So degrees Fahrenheit, degrees Fahrenheit. Let's see, 156.7, 167.3. 156.7, 167.3. You see? It's between the two. You see, with 95% confidence, you can say that the mean temperature of the coffee sold is between this and that. Notice, maybe you will even like this more, is that here they even write the conclusion for you. Look under the blue. You can be 95% confident that the population mean falls between, and they put the two values. But all what you have to do is not say the population mean, you will say the mean temperature of coffee sold. So you will just show that you understand that it's from the question that you get the answer. So related to the question. And here I show you how to do it using the online calculator. And again, the link is here. So you can use it with all the examples. And now we have, as usual, La'nood's multiple choice exercises, but only 2 exercises. And very quick, and you can solve them using the calculator or the t-table. The first one is on the t-table, and the second one is finding the confidence interval. So please solve these 2 and send me the answer. Let's just say that the right answer is D in 1. So please send me 1 is D with a screenshot showing that you used something. Either you used this calculator, the one here, or this calculator. Of course, this one is for just finding T. So you'll use this calculator and then send me. It's 1D because the screenshot of the calculator. And then you will solve number 2. And let's say that the right answer for 2 was C. So you'll say 2C, and then you will attach a screenshot of this lower half under the calculation. You see this here, the calculation. From here till the end, take a screenshot after you do. Don't forget to press calculate, by the way. It's very important. If you don't press it, it will stay on the previous question. Okay, and now you all know how to send screenshots. I've noticed that most of you now are professional at taking screenshots and at writing your answers. But I want to tell the students that are not taking my courses is when you send your professor to take screenshots, just like this. For example, this will make it easier for your professor to check your answers. They will know exactly what you entered here, 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 and why you got the answer that you got. So they can tell you, for example, your sample size, you entered 15, you thought it was the degrees of freedom, okay, and so on. Because it depends. Here they ask you for the sample size, not the degrees of freedom. But in the other calculator, I'll just go back quickly here. In this calculator, it asks for the degrees of freedom. So just be careful of doing this. So now we have the exercises. There are 7 exercises. I'm going to just stay 3 seconds on each page. So for those that didn't download the PDF of the lecture, those are not my students. My students will always print them out, and while I'm speaking, they're writing with me. But I'm talking about students that are taking the course with someone else and don't want to print them. Yes, it's okay, but at least for the exercises, please take screenshots and then answer and send to your professor. Okay, so here and here, and this is the last page. And thank you for watching. Please subscribe to my channel if you haven't done so yet. Put the notification on so whenever I post a video you get notified immediately. And the most important is please like this video if you feel that it helped you understand confidence intervals when sigma is unknown. And just one thing, there are 6 slides left for which La'nood is teaching you about how to use the gamma function to find the volume of balls in several dimensions. Dimension 1 up to infinity. She teaches you everything. So there are 6 slides here. Defines the gamma function, basic properties, what the graph looks like, and then she shows you the volumes up to a ball in dimension 10, and then she shows you the unit ball. This is the ball of radius 1. Look at the numbers here. First, in dimension 1, the volume is 2. In dimension 2, the volume is pi, which is 3.14. In dimension 3, it's 4 over 3 pi r cubed, but r is assumed to be 1. So you see 4.18, whatever. Then in dimension 4, look, it's 4.9. Dimension 5, 5.2. But now look at what's going on. In dimension 6, its volume is less than dimension 5. So a person who sees the first 5 dimensions would think that the volume increases with the more dimensions, but actually it starts decreasing, and you can show actually that the limit as the dimension goes to infinity of the volume of the unit ball is 0. Okay, so this shows you that we live in a finite dimensional space, because if we lived in an infinite dimensional space, we wouldn't have volume. Our volume would be 0. Okay, so nice application. And of course, it uses the gamma function, and she's trying to show you this. But you're not responsible for this if your course is only statistics. This is just done for students that want to learn more. So Li'anud always tries to help you learn more. Okay, but this is the last slide really for this lecture. So thank you for watching, and take care.